Hiya, folks. I'm just going to go into the discussion we had the other day about the shrinking dollar problem. And Fabrice made a question, what would happen? I think it was Fabrice made a point about what would happen if the measurements were had a built-in error to them. Okay, so let's imagine, so here's the original picture I gave you, 156 by 66 millimeters. Now, what about if we say, this is a little bit extreme. I don't think it would be this much, but there will be some fluctuation in the actual size of a dollar. Dollar dimensions, there has to be. You cannot produce billions of something all the same size. It's impossible. All machines are calibrated and their standard deviations are well known by the engineers that run them, especially in the US Mint. So there will be a value. We could probably find out if we Googled it, but I'm going to keep it as a millimeter, keep things simple as possible. So the dollar dimensions could be plus or minus 1 millimeter, probably more like 1 micrometer in reality, but on either side. So it could be 156 plus or minus 1, so 155 to 157, or 65 to 67. Now, I also decided, in light of my thinking about this task, this stuff here. So just read this, please. The longest side of the dollar will be the most visible. So I'm only going to work with length from now on. Okay, in the first solution I referred to the width because it was smaller. I shouldn't have done that. It was almost like I wanted it to be too small. But with hindsight, length is the most sensible side to choose. So when the length drops below my threshold of 0.04 millimeters, that's the point at which I will say the dollar becomes invisible. So just to show you some other good practice, I have in my Google Drive, rather than going over my previous solution, okay, I'm going to treat this as a learning point for you and for me, and I've now got a different version of the solution with errors calculated. Okay, this is a good idea with Google Drive. If you want to keep versions of your work, you can go back to it with versions in Google, but that's all a bit too high tech for me. I prefer just to have files I can see the different versions. Okay, I've also made a different copy of my spreadsheet. So when I go ahead and delete the width column because it's no longer of interest to me, I'm going to delete it. I could just hide it, but let's go ahead and nuke it. All right, now the length is the side. Oh, maybe I did refer to length in the original solution. Anyway, let's get rid of that. Easy enough. Actually, with hindsight, I think I'll keep that just because I can copy and paste the labels. What does that do? Okay, apologize if this is a bit bitty. I'm experimenting with Screencast-O-Matic. So what I did was I went up here, clicked the view mode. Bit of a slow internet connection here. Come on. So if you look at here, I think it's in view mode. If you click this little drop down, you can move to own sheet. And notice now we've got 2 sheets in our spreadsheet. So that's kind of cool. There for comparison later if we want it. Okay, I'm going to insert some columns here to do my other rows. Get back to you in just a second. I'm having all sorts of problems with the internet, so I apologize if this screencast is a bit odd. Let's continue. So we've said the lower bound, taking into account the error, could be as low as 155 millimeters. Now, I don't like all those decimal places there, but I haven't quite figured out how to stop that happening. Luckily, we're not getting them here though, because I haven't formatted this column yet. So we're just going to get all those unwanted decimal places. The upper bound is 157 millimeters. Now, that's after 0 copies, so it's the original size. So in here we'll put the formula. We're going to refer to cell C2 and we're going to times that by, it was 0.75. Now I want it to be to the power of 1. Instead of just typing 1, I'm going to hit this 1 here. So then when I copy this formula down, it will automatically copy this reference. This is called a relative cell reference. Okay, and when you move a formula, the relative reference moves along with it. So A3 will always be, well, you just watch what happens. I'll drag it down. You can probably just double click that little corner there. You can on Excel. Okay, you might be able to just double click it. Ah, there we are. So, oh, interesting. Now, Let's see how we're doing with this. Yeah, so this reads, there's a problem. Yeah. Now what I need to do, I'm talking about relative cell references. I thought it decreased a bit rapidly. Okay, there's a problem with the formula here. Now look, if I click this one here, you can see that it's referencing A4 rather than A3, but it's also referencing C3 rather than C2. So instead of taking the original size of the dollar, which is in C1, and multiplying that by 0.75 to the power of n, it's actually taking the value in the cell directly above it and multiplying that by the value of 0.75 to the power of n. Okay, that's an error. What I need to do to fix that is, well, I could either do this. I could either type in equals 155, okay, times that, but that's not so good. Okay, we're going to get a code dependency, if you like. Much better to do this, equals, and we're going to use $C $2. That's an absolute cell reference. That won't move when I copy the cell. Okay, and we're going to times that by 0.75 to the power of, to the power of n. And we do want that. That's a relative cell reference. That will move. Now let's see if we can just double click. No. Okay, and we'll copy it down, and this time we won't see such rapid decreasing. Okay, that's more like it. Okay, so we're going to compare this lower bound for our estimate for the size of this shrunken dollar with the value just using the center, the middle value in the bounds, if you like, or what you might call the average length. Okay, this is an important kind of concept actually. Anyway, you can see that in terms of its actual size, it gets down to 1 millimeter or so between, well, after the 18th copy, it's down to less than 1 millimeter in size, in length, and we're looking for 0.04 as the threshold of visibility. So after 28 copies, it's just about visible. After 29 copies, now it's invisible according to our defined threshold. Okay, I don't need to write that there. I could just write though the reasoning for that, because it's less than 0.04 millimeters. Okay, it's the first value which is less. We might just highlight that and say yippee. Maybe bolden it up as well. Okay, it all helps communication. Now we need to format this column and this column so we're not getting so many decimal places. So how do we do that? Got a very small screen here. It's not conditional formatting. It's just format number. Okay, so we're telling it it's a number, but we might also want to custom number format. That's what we want. And we want how many decimal places? Oh my word, what's going on here? These are all a bit freaky. We're just going to go for this one, I think. I don't know what that's going to do. Oh, it's rounding to integers. That's not so helpful. Everything rounds to 0 after a while. Okay, I'll have a little play and get back to you. So after much hunting, I had to go online and find a solution. Couldn't figure it out, so I highlight these cells, and it was here. It's this 1, 2, 3 drop down, and I just went for scientific because I think that's pretty good for this actually. And it's also the way the TI-84 calculator displays very big and very small numbers, so it's good to get used to. They omit the plus, but they do include a negative if it's negative. So this is 155 basically, 1.55 times 10 to the power of 2. So the E stands for times 10 to the power of. Okay, so I think that's quite a good format. And so we're looking for, is that easy to see there? I guess so. We can see that that is 0.004 something, because the minus 2 there means you have to put the decimal place, move it 2 spaces to the left. So we get 0.049, so we can see that's greater. And that's easily visible as less than. So this scientific is a good format here. Probably should do this column like it as well, just show you how easy it is. Tink. Now they're easier to compare, of course, because they're, yeah, look, it's much easier to compare out by about, well, it's not, it looks like 200s, right? These two numbers here look like they differ by 200s, but it's not actually 200s, it's 200s times 10 to the minus 1, so it's 2000s, actually. 2000ths of a millimeter, also known as 2 millionths of a meter, or 2 microns, 2 micrometers. Anyway, so that's the lower bound calculated. We'll just take this upper bound and we'll enter the formula. So we're going to take the absolute cell reference of D, another $sign, 2. Okay, you could learn more about how this works, but just remember that it's dollar column, dollar row for an absolute cell reference. We're going to multiply that. We use the Shift 8 key by 0.75 and then Shift 6 to the power of, and we want to reference N. So we click that, and we want that cell reference to be relative to move. Let's copy her down. And let's see if there's any difference in where the threshold value occurs. No, not a difference at all. Okay, so not a huge amount to talk about. There it is. It goes after 30 copies to 31 copies. And it's got a fairly small difference there. Now, so you might think, oh, well, this is, it's a real world problem. We're trying to find ourselves a level 8 example. How can we explain these differences? Okay, let's go for a level 5, 6 first. Have a little pause and think about it. I'm going to do the same. So it's a very good question. Anyway, let's have a think about this. The smallest thing visible with an optical microscope, that's one that uses light rather than, an electron microscope, is 1/5 of a micron. 1/5 of a micron is 0.000. Actually, that's not right, is it? 1/5 of a micron, 1,000th of a millimeter. Yeah, that is right, actually. Yeah, because that would be 2,000ths. Yeah, that's right. Yeah, 0.001 would be 1 micron. Okay, so what I did was I just extended my table down, and this time we're looking for, where is it? 0.0002 of a millimeter, which is 2e to the minus 4. Okay, using our scientific notation. So we scroll down, and we find that after 47 copies, the lower bound for the length it drops from, oh, I've highlighted the wrong column there actually. Should be column 48 that we're looking at. Okay, so after 48 copies, it goes from being greater than 2 times 10 to the minus 4 to less than 2 times 10 to the minus 4. And the same thing is also true with the upper bound for the length. So even at these dimensions, it doesn't make any difference at all, this error. Okay, so we are actually explaining our differences, we're discussing the differences verbally right now. There's also something else, I'm not finished yet, don't worry, but there's also something else I'd like to point out here. Now, you may be thinking, there's no way we were expected to do this, is there? Of course there isn't, but I'm just showing you that, the kind of way we can think about stuff. I wouldn't expect you to do this on your own, but I'm sure you can see what I'm doing and, think about it. So what we've shown is that even though there's quite a large gap in the dimensions of the dollar, I mean, it may not sound like a lot, but it's 1 millimeter, remember? We're now talking about 2 times 10 to the minus 4 of a millimeter, which is a tiny, tiny fraction of a millimeter. So how come that great big difference of plus or minus 1 millimeter at the top here, that's a much bigger difference. Let's have a look at how these graphs are behaving. This is going to be interesting, I promise. So we're going to, let me just get back to you when I've done the graphs. So what I'm trying to show you here is something about exponential decay. We're all used to exponential growth taking off, right? We know that we've plotted a few graphs now. We know that if we plot power graphs, they really do start to get very steep gradients over here, start to rise very rapidly. But this one is, well, it's a reflection, isn't it? It's like almost like a vertical reflection of exponential growth. And this is how exponential decay works. It's when you have negative powers of x, or when the base is got a magnitude less than 1, you get, instead of takeoff growth, rapid growth, you get steady decline. But the thing about this to notice is instead of getting faster, it actually gets slower. Okay, as we go along at the start here, the drops are much more rapid, the gradient is much steeper here, and then as the decay continues, as the number of copies increases, it actually, the rate of decrease gets slower. And so the changes in size made as we go from copy to copy are actually smaller. Just another point, actually, I should really have just plotted points here rather than a continuous line, because the dollar only really exists for a continuous line. The dollar size only exists for discrete values of n, I should say. Well, I couldn't get rid of the line, but I did manage to get points plotted. So this graph should only really exist for the points, because it's a discrete series there. Just to insert a chart, we go click on